Alright, so you're going to have to know the old IMA, AMA, and efficiency equations, and then the gear ratio ones as well. So we're going to have IMA, and what are the two things IMA can equal? Yep, so effort distance over resistance distance. Anybody remember the other one? Yep. So resistance force ideal over effort force ideal. And then what does AMA equal? Force resistance over force effort. And efficiency is what over what times 100? AMA over IMA times 100%. Goes down a little bit. And then for gear ratio, we kind of have one big long equation. We can use two parts of it at any point. So gear ratio equals N out over N in. And what is N? Does anybody remember? Number of teeth, yeah. And you can have diameter out over diameter in. We can also have radius out over radius in. So as long as you have it in the radius or the diameter, you just both need to match. Anybody remember? Oops, that's backwards. Don't write that down. Anybody remember what that symbol is? What does that represent? That one is angular velocity. That's going to be in something like RPM, rotations per minute. So that's how fast it's actually rotating. And last one, that Greek letter tau is torque. It's measured in foot-pounds. Alright. Do you guys have any questions on those equations? And again, you can use like two of them at a time. So you can use gear ratio and torque, or distance out over distance in and torque, or that and that. So you can just use two sections of this at a time. Does that kind of make sense to everybody? The first problem here, it should say a handicap ramp, not unhandicap ramp. A handicap ramp has a height of 2.8 feet and a slope that is 10 feet long. If a person in a wheelchair has a weight of 155 pounds, what is the ideal effort force? So we're looking for ideal effort force, and we have distances. So we're going to kind of set up an equation like this. Effort distance over resistance distance equals FR ideal over FE ideal. Alright, so what is our effort distance here? How far do you actually push up the ramp? 10 feet. And 2.8 feet is how high it actually goes, so that's the resistance distance. That makes sense to everybody? Difference between those two. And 155 pounds, is that a resistance or effort force? Resistance. And that's over effort force ideal. And so you're going to cross multiply and then divide. What do we get for our ideal effort force? 43.4. And that's pounds. On that. Any questions on that one? Alright, a wedge has a 1.4 inch cutting blade that should be a 1.4 inch wide cutting blade that is 1.4 inches long. What's the ideal mechanical advantage of the wedge? So remember when we looked at the wedge, this is our effort distance, and this is our resistance distance. So to find IMA, what is our resistance distance going to be? Yeah, 1.4. I don't know why I asked her that first. And what is our effort distance going to be? 4.1 inches. So we divide that out, what do we get? 2.9 is our mechanical advantage. Any questions on that one? Third one is a screw problem, which are kind of the trickiest ones of the basic simple machine problems. We still use IMA equals effort distance over resistance distance. Alright, what is our effort distance going to be? Remember, we want to figure out the distance we have to turn it to go one rotation. So if the distance the force has to go to turn one rotation if we're using a 3.6 inch long wrench. So if you turn a circle, how can you figure out the total distance it goes? 1/4, you're on the right track, but not for this part. So to find out our effort distance, it's going to be the circumference of the circle you make with the wrench. Does that make sense, everybody? So what's the equation for circumference of a circle? 2 pi r, and our radius is just going to be the length of the wrench in this case. So it's going to be 2 pi times 3.6 inches. Any questions on that part? Now, this number right here, this 30, gives us the threads per inch. What we want to figure out is how far down the screw goes if you turn it around one time. So if you turn it around one time, it's going to go basically through one thread. So to figure out how many inches it goes down, it's 1 divided by that number. So every time you turn it, it's going to go down 1/30th of an inch. So that's what our equation is going to look like for IMA. Do you guys have any questions on that equation before we go on? What do we get for our IMA here? Oops. 678.6 for our ideal mechanical advantage. And that makes sense. Remember, screws are going to have really large IMAs. Their efficiency is usually very small as well. Very small though. Any questions on this problem? There's a gear ratio 1. If gear A drives gear B, if the torque on gear B is 12 foot-pounds, what is the torque on gear A? So what do we have here? We have our torque on A, or torque on B, due to 12 foot-pounds. And from this picture, we know the number of teeth, right? Somebody count the number of teeth on B. All right, everybody count them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So number of teeth on B is 18 teeth. And how many teeth on A? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Teeth on A is 12 teeth. Alright, so what we're going to set up here is we're just going to use part of the big long gear ratio equation. So we're going to use the teeth out over the teeth in and set that equal to the torque out over the torque in. Does that make sense to everybody? So we're going to say an out over N in equals torque out over torque in. And which is our output gear here? So gear A drives gear B, so B is going to be the output gear. So we're going to say number of teeth out is 18, number of teeth in is 12, the torque out is 12 foot-pounds, and we're looking for the torque in. Alright, so it wouldn't let me record on that other slide for a second, so we'll just do the rest here. So what was the answer to that for the torque on A? 8 foot-pounds. Any questions on that one? Alright, last one we'll do together. This is a gear train problem. So we have 4 gears here, and none of these are idle gears because these two are on the same shaft. So if gear 4 is the input gear, what is the overall gear ratio for the gear train? So we get gear 4 has 15. So what we're going to do is we're going to do the gear ratio between 4 and 3, and the gear ratio between 2 and 1, and then multiply them together to get the total gear ratio. So the first thing we're going to find is gear ratio of 4 and 3, and our gear ratio is teeth out over teeth in. Right. So which one is our output gear, 3 or 4? 3. So how many teeth does 3 have? So 10, and gear 4 has 15 teeth. So what's that equal? 2/3 are 0.67. So that's our gear ratio between 3 and 4. Now we're going to find the gear ratio between, the gear ratio between 2 and 1. And remember that when we say the 4 is the input gear, that means everything kind of goes this way. So what is our output gear for what between 1 and 2? 1. So 1's got 5 teeth, 2 has 20. So what's that gear ratio going to be? 0.25. Now to find our gear ratio total, the gear ratio for 3 and 4, or for 4 and 3, times the gear ratio for 2 and 1. So we get 0.67 times 0.25. And what's our total gear ratio? 0.1675. Any questions on that one? Alright.